Display A. Display A is devoted to the study of alpha rays. Rutherford discovered the heterogeneous nature of the radiation emitted by radioactive materials in 1898. While still a graduate student in Cambridge, he called the readily absorbed component alpha rays and the more penetrating component beta rays. The particle nature of the beta rays was easily demonstrated, since they could be deflected in electric and magnetic fields, and it was shown that they were electrons. But prior to 1902, the nature of the alpha rays was unknown. It was assumed that they were charged particles, but this was unproven because they could apparently not be deviated in a magnetic or electric field. Rutherford suspected that a very strong field was needed to deviate the alphas, and he designed the apparatus accordingly. The series of apparatus on the left side of the display case are the first apparatus Rutherford used to demonstrate the magnetic and electric deviation of alpha rays. The alpha rays from a layer of radium salt pass through a set of parallel brass plates into a gold leaf electroscope. An electroscope is a simple device for detecting the presence and determining the sign of electric charges by means of electrostatic attraction and repulsion, often between two pieces of gold leaf. When a strong magnetic field from an electromagnet was applied across the plates, the reading of the electroscope substantially decreased. This proved that the rays were charged particles. By half covering the exits two parallel plates, as shown by the third set of plate, such that the open portion was to one side, the direction of the deviation, and hence the sign of the charge, could be determined. This showed that the alpha particles were positively charged, and fairly good values of the ratio of their charged mass and velocity could be deduced. In 1906, Rutherford used the third apparatus in the display to verify his assumption that the mass and ratio of charge to mass of all alpha particles is the same. This required the determination of the charge to mass ratio for different sources of alpha particles, derived from radium A, polonium-218, radium F, polonium-210, actinium, and thorium. The value of ratios obtained in each case was the same, within the experimental error. Furthermore, the charge-to-mass ratios remained unchanged within the large experimental error, even after the particles had passed through the screens of mica and aluminum equivalent to 6.5 centimeters of air. After emerging from the deflecting plates, the alpha rays reached a small photographic plate and, with a very long exposure, several days, in fact, gave an image of the line source. By reversing the voltage at intervals, the image was split into two, the separation of which depended on the voltage and the geometry of the apparatus. A voltage of 500 volts and a gap of 0.21 millimeters between the plates resulted in images about 2 millimeters apart, as seen in the data at the left of the apparatus. By careful measurement of the image separation and by adding data on magnetic deflection in addition to electric deflection, Rutherford was able to calculate the charge-to-mass ratio. The value thereby obtained was 5.1 times 10 to the 3 electromagnetic units, half that of the hydrogen ion obtained by hydrolysis of water. Rutherford listed three possible identities of the alpha particle consistent with this finding. His preferred identity was that of a helium atom carrying twice the ionic charge of hydrogen, but the final proof of this had to wait until 1908, when he moved to Manchester and was able to carry out an experiment in which the identity of helium was demonstrated spectroscopically. Display B. Cabinet B presents some apparatus used by Rutherford in studies using emanation, that is, the radioactive gas emitted by thorium. In 1899, Rutherford observed that the radiation from thorium oxide was not constant but varied in a most capricious manner. The compounds of uranium, on the other hand, remained constant. Rutherford concluded that thorium compounds continuously emit radioactive particles which retain their radioactive powers for several minutes. Rutherford called this emission emanation. At about the same time, Pierre and Marie Curie observed a similar phenomenon with radium, except the gas emitted by radium, which they called radon, remained radioactive for a month. The apparatus shown at the top right is an ionization chamber, a typical detector used by Rutherford. Ionization is the complete loss of an electron from an atom. The resulting positive atom is called an ion. An ionization chamber is a volume where an electric field is present between two electrodes. If ionized atoms or molecules are present, the electric field will result in a current that can be measured with an electroscope. The chamber shown here was used to study the condensation temperature of thorium emanation. A current of air, passing through a tube containing thorium oxide, carried thorium emanation through a series of filters ending by a copper helix and then into the ionization chamber, producing a current due to the ionization from its decay. when the metal helix was immersed in liquid air in a Dewar flask. The reading of the electrometer ceased, indicating that the emanation had condensed at the low temperature in the flask. After removing the helix from the flask, the ionization current gradually returned as the emanation was restored to a gaseous state. The temperature at which the emanation condensed was determined by measuring the voltage across the helix when a constant current was sent through, and hence calculating its resistance. The helix used for this purpose is displayed in Cabinet E. The long ionization chamber at the bottom left was used to measure the rate of decay of the emanation. The three electrodes, A, B, and C, were of equal length and located on the axis of the ionization chamber, and an insulating key was arranged such that any one of the electrodes, or all three together, could be connected to the electrometer. With an air current flowing from the left to the right at about 0.8 centimeters per second, the current to electrode C was about twice that to electrode B, and this corresponds to a half-life of about 1 minute for thorium emanation. Rutherford and Soddy observed that the ratio of current measured at the three electrodes was such that the ratio of current A divided by the current at B was always equal to the ratio of current B over the current at C. This could be understood if the decay probability is constant with time characteristics by its half-life. Rutherford and Soddy used such data to establish what is today called the radioactive decay law. The ionization chamber at the bottom right was used to evaluate the molecular weight of radium emanation. At first, it was thought that emanation was simply thorium or radium in vapor form, but the amount available was far too small to carry out chemical or even spectroscopic tests. Rutherford, in collaboration with Harriet Brooks, therefore decided to estimate the molecular weight of radium emanation by measuring its rate of diffusion in air. He used radium rather than thorium emanation because the former had a reasonably long half-life and was therefore approximately constant throughout the experiment. The long cylindrical ionization chamber was divided into two by a sliding metal gate. With the gate closed, air-containing emanation was injected into the left-hand chamber, and readings of the ionization current were made with the electrometer. When the electrometer reading became constant, the supply of emanation was stopped and the sliding gate opened. Eventually, the two chambers showed equal ionization currents, indicating that the emanation was uniformly distributed between the two chambers. Analysis of the time sequence indicated that the molecular weight of the emanation was between 40 and 100. This showed that the emanation could not be radium in vapor form, since Madame Curie had already shown that radium was an element of atomic weight of at least 140. Actually, this result was quite wrong. The experiment was subject to many errors and uncertainties. If Rutherford and Brooks had obtained the correct answer, that is 222, and had known that the atomic weight of radium is 226, he might have concluded that the emanation was indeed radium vapor. As it was, the result constituted an important piece of evidence supporting the transmutation theory, which was beginning to take shape in Rutherford's mind. Display C. Cabinet C presents the research of Rutherford on something he called excited radioactivity. In the summer of 1899, Rutherford observed an unexpected phenomenon. A substance which has been exposed for some time in the presence of thorium is itself rendered radioactive. Rutherford soon ascertained that this is due to the deposition on the surface of the exposed substance of an invisible layer of radioactive material. This excited radioactivity decayed fairly rapidly and disappeared within a few days. The excited, or induced, radioactivity of radium was independently observed by the Curies at about the same time. The two ionization chambers on the left constitute a related pair. They were used to establish the relationship of emanation and excited radioactivity. A current of air containing radium emanation was passed through to the top cylindrical ionization chamber. The openings of the chamber were then closed, and the ionization current due to the emanation was measured. After several hours, the excited activity on the central electrode reached a maximum, and the rod was then removed and placed in the bottom identical chamber so that the ionization due to the excited activity could be measured, together with its rate of decay. At the same time, a fresh central rod was put in the first chamber, and the ionization due to the emanation was measured. For radium C, that is bismuth-214, the ionization due to the excited radiation was found to be 50% greater than that due to the emanation which causes it, while for radium E, that is bismuth-210, the excited radiation was only about half that due to emanation. The large apparatus at the center of the cabinet comprised a rectangular wooden vessel, 60 centimeters in length, with a single U-shaped anode and 4 independent cathodes. It was used to study excited radioactivity produced by thorium emanation. A layer of thorium oxide covered with paper was placed at one end, and a steady current of air, about 12 centimeters per minute, passed through. The current due to emanation was measured at each electrode, and since thorium emanation has a half-life of about 1 minute, the currents on the successive electrodes were only 55, 18, and 7% respectively of that at the first electrode. After 7 hours, the flow of air containing emanation was stopped, and the ionization current due to the excited activity on each electrode was measured. This was found to be approximately proportional to the current due to emanation in each case. The apparatus on the top right is a small cylindrical ionization chamber used to study the dependence of excitation on metal and sign of charge. It has a removable central electrode. The activity excited by a flow of emanation was measured on central electrodes of various metals, and with this electrode charged positively and negatively. It was found that the excited radioactivity was independent of the nature of the electrode, and that this activity was greatest when the electrode was negatively charged. The apparatus on the bottom right was used to study the dependence of excitation on pressure. It comprised a brass cylinder with the ebonite stopper through which passed a brass rod. The cylinder was connected to a mercury pump. Thorium oxide in a paper envelope was placed inside the cylinder. The apparatus was rapidly exhausted to the required pressure and the rod exposed for several hours. The rod was then removed and placed in another ionization chamber so that its radioactivity could be measured. The results showed that the excited radioactivity is independent of the pressure down to 16 millimeters of mercury. Cabinet D. Cabinet D contains apparatus which Rutherford used to study the energy involved in radioactive transformations and in the production of an ion in a gas. The apparatus shown at the bottom left was part of an experiment to determine the energy required to produce an ion in air. 2 identical strips of platinum, each 3 meters long and 5 millimeters wide, were wound on mica frames. One grid was irradiated by X-rays for a given time, and the change in resistance of grid A compared with grid A prime, unirradiated, was measured by a Wheatstone bridge. The resistance change was calibrated, in terms of heating effect, by passing a known current through the coil for the same period of the X-ray exposure. An ionization chamber was used to determine the absorption coefficient of the X-rays in air, and secondly, to measure the intensity of the rays before and after passing through the grid A. The fraction of the energy absorbed in the platinum, and its absolute amount, could be determined, and thus the amount of energy producing ions in the known volume of air could be calculated. It was assumed that the X-ray energy absorbed in air was entirely expended in producing ions. This experiment gave a value of 100 electron volts as the energy required to produce an ion in air. The modern value is around 34 electron volts. Rutherford and Barnes used the apparatus at the bottom right to measure the heating effect of radium and its emanation. The differential air calorimeter comprised 2 identical glass flasks, connected with a manometer containing xylene, and was immersed in a constant temperature water bath. A sealed tube containing a known mass of radium, or its emanation equivalent, was inserted in the vertical tube in the right-hand flask. The radiation emitted caused a rise in temperature and hence an expansion of the air in this flask, and thus the displacement of the xylene in the manometer. This displacement was calibrated by means of a measured current and a known resistance wire in the left-hand flask. The experiment showed that 1 gram of radium, in equilibrium with its products, produced 110 gram calories per hour, of which more than 2/3 was due to the emanation stored in the radium. The heating effect of the radium from which the emanation had been expelled was found to increase exponentially, while that of the separated emanation and its products decreased exponentially, and the total was always equal to the amount from the original radium before de-emanation. The energy emitted corresponded closely to that of alpha rays. Rutherford and Barnes concluded that the matter under special conditions is capable of emitting an amount of energy enormous compared with that released in the most intense chemical reactions. This energy is derived from the energy latent in radium atoms and is released in the successive stages of their disintegration. The differential air calorimeter discussed above was used for long-term observations. over several weeks, but did not respond quickly enough to measure the initial changes involved in the decay of emanation and the production of excited radioactivity. For these effects, Rutherford and Barnes constructed a number of sensitive platinum resistance thermometers which responded to temperature changes within a few minutes. Examples of those are shown at the top left in the cabinet. Differential platinum resistance thermometers were made by fusing coils of fine platinum wire in the inside of thin glass tubes 5 millimeters in diameter. Tubes containing radium or emanation were made to slide into the interior of the coil so that the resistance wire was in direct contact with the glass envelope containing the source of heat. The glass bath was kept at a uniform temperature by stirring. Changes in the resistance of a thermometer when a radium or emanation tube was inserted was measured by means of a bridge circuit. The greatest difference in the observed temperature was 0.3 Celsius, but readings could be made down to 0.003 degrees Celsius. The initial drop in heat emission from radium was due to the rapid decay of the active deposit left behind by the emanation. The initial rise from the emanation arose from the formation of an active deposit by the emanation. The helix at the top right is related to the measure of the condensation points of emanation discussed in Cabinet B. Rutherford and Soddy used this apparatus to demonstrate that thorium emanation could be liquefied and was therefore a true gas. It was used to measure the precise condensation points of both thorium and radium emanations. Thin copper tubing was wound into an inner spiral of mean diameter 1.8 centimeters and an outer spiral of mean diameter 2.9 centimeters. The turns of the outer spiral were separated from each other and from the inner spiral by air spaces. The outward spiral constituted a thermometer. With a constant current of 0.9 milliamps, the voltage across the spiral dropped from around 6 millivolts at this room temperature to less than 2 millivolts at the temperature of liquid air. The purpose of this arrangement was to subject the emanation stream to a preliminary cooling to the desired temperature in order to ensure that the measuring outer spiral was not heated locally by entering gas stream. The liquid used in the tube was liquefied ethylene, which is liquid between negative 104 degrees and negative 169 degrees Celsius. The condensation points thus determined were negative 120 degrees Celsius for thorium emanation and negative 150 degrees Celsius for radium emanation. Display E. Cabinet E contains a number of apparatus used for the study and measurement of alpha, beta, and gamma rays. Rutherford used two principal methods for measuring the intensity of the radiations emitted by a radioactive substance. First, he used a gold leaf electroscope that is comprised of a metal box containing an insulated metal rod to which was attached one very end of a very thin gold leaf. An example is shown in Cabinet A. An alternative measuring instrument was the quadrant electrometer, shown here on the top left corner. The electrometer comprised a flat cylindrical metal box divided into 4 insulated quadrants. A light metal paddle was suspended inside the 4 quadrants by a thin wire, and movement of the needle could be observed on a scale by a light beam reflected by a small mirror attached to the suspending wire. One pair of opposite quadrants was connected to Earth, the other pair to the electrode of an ionization chamber. The ionization current in the chamber altered the potential of the electrode and hence of the quadrant pair to which it was connected. This resulted in a movement of the needle which translated into deflection of the light beam. The quadrant electrometer devised by Dolezalek in 1901 was particularly sensitive. For working with a quadrant electrometer, it was found necessary to use a special remote control key for making and breaking the connection to Earth of the quadrants. The key shown at the right of the electrometer comprised a brass tube which could be moved up and down within a rigid support, thereby making or breaking contact with the mercury ball. The movement was controlled at a distance by the cord attached to the pulleys. The 3 large cylindrical apparatus at the bottom of the cabinet are various electroscopes used to measure the ionization produced by different types of radiations. The first apparatus to the left was used to study ionization in different gases. The ionization was produced by a thin layer of radium or uranium on the lower plate. The distance and potential between the parallel electrodes could be varied, and the potential at intermediate distances were measured by a wire loop connected to an electrometer which could be adjusted to 0 by means of a rheostat. The ionization current was determined for dry and moist air, and after the introduction of alcohol vapor or the vapor of methylleodide. The ionization in the two detectors on the right hand was observed by a gold leaf electroscope. In the first detector, the separation between alpha, beta, and gamma rays was obtained by moving the source relative to the various absorber present. For example, for gamma ray measurements, the source was placed under a lead plate 6 mm thick, which completely absorbed the alpha and betas but allowed the gammas to pass. The last detector to the right was used for measuring small amounts of radium in the presence of emanation. The emanation in equilibrium with the unknown small amount of radium was extracted, mixed with air, and introduced into the partly evacuated electroscope. The resulting rate of fall of the gold leaf was compared with that produced under the same conditions by the emanation from a radium standard. As little as 10 to the negative 8 milligrams of radium could be measured by this technique. The large apparatus at the bottom center was used for producing variable currents of known magnitude. There was a need for a method of producing a constant deflection of the electrometer proportional to radium intensity for the study of radioactive elements which decayed very rapidly. This instrument solved the problem by balancing the unknown ionization current against the current generated in a second parallel plate chamber, in which the lower plate was coated with a layer of radioactive material of a long half-life. The area of uranium opposite the upper electrode was varied by sliding the lower electrode, to which a calibrated scale was attached. The two small apparatus at the top right were used to study the effect of heat on excited radioactivity in the generation of fluorescence by alpha rays. Around 1900, many experiments were done to try to modify the radioactive properties of the elements. In the apparatus to the right, the active deposit of thorium emanation was collected on a platinum helix in a closed vessel. When the wire was electrically heated to incondense, the activity was apparently destroyed. However, further investigation showed that the active deposit was not destroyed but simply driven off the wire and deposited on the cool inner surface of the vessel. Rutherford showed that radiation can induce fluorescence in various crystals. Radium emanation mixed with air was introduced into the glass vessels. The alpha rays from the emanation excited brilliant fluorescence of various colors in the glass or in the crystals enclosed. Rutherford showed that the effect was due mainly to the alpha rays. Display F. Cabinet F is a triangular table at the entrance to the museum. This display cabinet houses two separate exhibits. On one side is a series of 12 sections showing the materials used by Rutherford in July to December 1904 to elucidate the decay series of radium beyond the stages of the excited radioactivity discussed in Cabinet C. Each of these sections include original dated labels in Rutherford's handwriting. Rutherford suspected that some activity persisted after the decay of the short-lived deposit, and he carried out a series of experiments to investigate this problem. For example, in the first section, 6 equal plates of different metals were exposed to emanation. After several weeks, all of the plates showed equal traces of residual activity, which increased at least threefold within a month. Rutherford concluded that there must be a common active deposit rather than an induced effect, and the gradual increase suggested that there was a presence of a rayless parent body. As a result of these experiments, Rutherford identified 3 decay products which he designated as radium D, E, and F. He found no evidence of an active product beyond radium F. The atomic weight of radium was measured to be 225, and its products emitted 5 alpha particles: radium, radon, radium A, radium C, and radium F. Assuming that the alpha particles was a helium atom of atomic weight 4, Rutherford concluded that the end product of the radium series had an atomic weight of 205. This was so close to that of lead 206 that he concluded as most probable that the final product of radium decay was stable lead. A number of documents are displayed on the other side of the cabinet. It includes Rutherford's Curriculum Vitae, 1894 to 1907, a handwritten document probably written in late 1906 when Rutherford had decided to return to the UK. A transcript and discussion of this document was published by Cohen in 1995. One knot in the CV, the name of Otto Hahn, who had been at McGill in the period 1905 to 1906. A draft in Rutherford's handwriting of the obituary of Professor John Cox, chairman of the Department of Physics from 1890 to 1909. The obituary was published in Nature June 16, 1923. A centenary Canadian postcard issued on 24th of March 1971 in honor of the 100th anniversary of Rutherford's birth. A photocopy of Rutherford's letter to Sir William Crookes, dated April 29, 1902, with which he encloses a copy of his first paper with Frederick Soddy announcing the theory of spontaneous transmutation. Center table. On the top of the center table is the first book of the series of 3 books entitled The Collected Papers of Lord Rutherford of Nelson. The full collection is in the bookcase near Cabinet D. The last part of the first book on the center table contains copies of the 69 scientific papers written by Rutherford while at McGill. On one side of the center table is a sample of these papers. Among this sample, one should know 2 of the 9 papers written by Rutherford and Frederick Soddy during their 18 months collaboration at McGill are displayed. The displayed papers describe the most important discovery of Rutherford at McGill, that radioactivity is a transmutation process. A highlight from one of those displayed papers is the statement that the position is thus reached that radioactivity is at once an atomic phenomenon and the accompaniment of a chemical chain in which new kinds of matter are produced. The 2 considerations force us to the conclusion that radioactivity is a manifestation of some atomic chemical change. Note that this breakthrough discovery was not easily accepted by many famous physicists. Due to the important discovery, McGill has been identified by the American Physical Society in 1909 as a historic site in physics. At this occasion, APS presented a pair of plaques, one in English, one French, to McGill University in Montreal to honor the achievements of Ernest Rutherford and Frederick Soddy. The English plaque reads, "At this location, Ernest Rutherford and Frederick Soddy, during 1901 to 1903, correctly explained radioactivity as emission of particles from the nucleus and established the laws of the spontaneous transmutation of the elements." At the bottom left is found the only paper Rutherford wrote on radioactivity before joining McGill. This paper was submitted to the journal by J.J. Thomson as Rutherford was on his way to McGill. It is in this paper that he reported that there is more than one type of radiation. He writes, "These experiments show that the uranium radiation is complex and that there are present at least 2 distinct types of radiation. One that is readily absorbed, which will be termed for convenience the alpha radiation, and the other of more penetrative character, which will be termed the beta radiation." At the top left is a paper by Rutherford and Harriet Brooks, who was the first graduate student of Rutherford at McGill. She was the first woman at McGill to receive a master's degree. She is considered one of the leading women in her time in the field of nuclear physics, second only to Marie Curie. In 1902, she came back to McGill as a lecturer in the Royal Victoria College, the McGill Women's College. This paper makes the statement that these numbers exclude the possibility of the substance being a vapor radium. We must therefore conclude that the emanation is in reality a heavy radioactive vapor or gas. To the right of Rutherford's and Barnes' paper is a paper by Rutherford and Otto Hahn. Otto Hahn, best known for his discovery of nuclear fission in collaboration with Meitner and Strassmann, was a junior researcher at McGill in 1905 to 1906. At McGill, he discovered thorium-C, later identified as polonium-212, radium-D, later identified as lead-210, and radioactinium, later identified as thorium-227, and investigated the alpha rays of radiothorium. The other side of the table presents various other documents. Among the items shown is a copy of the New Zealand $100 bill that includes Rutherford's portrait. A copy of the real bill is shown in the bookcase near the table. It is close to 100 Canadian dollars. A series of stamps emitted in honor of Rutherford is also presented. There are also, in fact, many other stamps that have been produced. The table also contains a photo of Professor Ferdinand Freddy Turreau, who founded the museum and was its first curator. At the time, the museum was in the old physics building where Rutherford worked. Professor Turreau has worked in the Cavendish laboratory at the time Rutherford was there. Before leaving, you are invited to sign our signing book that is on the central table. Thank you for your visit.